The purpose of this lab is to capture a falling object using Tracker and then use Newton's second law in the Python application to analyze the effects of gravitational and drag force on the acceleration of an object. Here we can see that as the ball travels downwards along the negative y-axis, its acceleration continues to increase. This can also be modeled by the graph shown on the right side of Tracker. First, we ran a code that only factored in gravitational force. To do this, we inserted the mass of the object into the code and then calculated the weight magnitude, which can be found by multiplying the ball mass by the force of gravity and the unit vector in the opposite direction of the ball, 0, 1, 0, which can be found here. Below you will see some other calculations that were not used in this code, but will be discussed later. Here we can see the results of this code plotted against our experimental data. The model data accelerated considerably faster and therefore traveled a further distance. This proves to us that there must be other forces acting on the object falling, which we will analyze further as we continue throughout the lab. Next, we will create a code that integrates drag force as well as gravitational force. The goal of doing this is to equate the correct net force so the acceleration of the model graph matches our experimental graph. To do so, we must add a drag force formula to the code, which can be found by squaring the magnitude of the velocity and then multiplying it by the unit vector j hat and the proportionality constant for the magnitude of the drag force. The purpose of the proportionality constant, b, is to create the correct output value for the final position in the model graph with drag force. While the initial position and final position may be correct, that does not necessarily insinuate that the positions in between will be. Here's the graph that shows all three plots together. As you can see, while the drag force matches well at the beginning and the end of the graph, we can see that the acceleration in between still doesn't quite match. This is most likely related to an improper calculation in the magnitude of the drag force. Our last step before running the code is adding arrows to our module. In order to do that, we'll set arrow1.pos and arrow2.pos equal to the initial ball position. Then we'll set arrow1.axes and arrow2.axes to the weight times the arrow scale and the drag force times the arrow scale. Arrow scale will simply produce the correct length in the module after it's run. Here's the code. As you can see, as the graph falls, the gravitational force stays constant, while the drag force increases gradually. Towards the end of the graph, the drag force begins to equate to the gravitational force. This shows that it is likely that the ball reached terminal velocity, or constant velocity, due to the F net equaling 0. In summary, Newton's second law was demonstrated through the Python application by predicting the motion of a falling object based off calculated weight forces and drag forces. While the lab did successfully show Newton's second law, there was some sources of error. These sources of error include distortion of video, image quality, mass of the ball, and human error. The video being distorted likely caused certain data to be skewed, creating imprecise results after the prediction in Python. Poor image quality made it hard for Tracker to trace the path of the image as it fell, also creating imprecise data. If the mass of the ball was taken incorrectly, or the scale used had some error, the weight force calculated would have been incorrect, also throwing off the data and the prediction made in Python. Finally, if any force was put on the ball as it was dropped, the ball would have accelerated faster, as well as reaching its terminal velocity faster, throwing off the data of the lab.